Okay, so what we talked about last time was we could have a wave function for hydrogen that's going to have some N, some L, and some M sub L. Right, and that's going to be, this function that we write down is going to be a solution to that large Hamiltonian that we looked at that has the three-dimensional motion and the electric potential attracting it. It's going to be in terms of some r, theta, and phi. And we recognize that through separation of variables, we can write this down as some r that depends on n and l, that only depends on the radius portion. And we can have some y that depends on L and M sub L for our angular parts, theta and phi. So we've got our radial parts and we've got our angular parts. To relate this to things that may be familiar, we actually start, when we start writing down these functions, we start giving them names. So if we have an R10 of R, so here, let me write this in 3 different bits. I'm going to switch colors to make it dramatic too. If we have a Y100 for our R theta phi, that would be an R10 of R, a Y00 of theta and phi. And we want to come up with some shorthand for how we refer to this. We end up calling this a 1s. Then we can do the same thing for like a Y20 of R theta phi. This is going to be R20 for the radial part, Y00 for the theta and phi. Since the y part is the same, since the angular part is the same, we still use this s bit. But since it's the R20, we call this a 2s. We can keep going. Sorry, that should be size on this side. Woof. Size on that side, not y's. Then we can have our psi of 210 And since now our y part has changed, we give it a different labeling. Since our n is still the same, that becomes our 2pz. Right? Because that m sub l equals 0, that's going to give us our everything in terms of like just the z component. We can write down something. Now the 2p x is going to look a little bit different. Right, and actually, I'm going to go ahead and just label this one rather than putting the 210. I'm going to just label this side 2px because it turns out the numbers we use are not as clean. As you know from the worksheet that we were doing, if I want this function to be real, so I can talk about some real component here, this is going to be an R21 of R times a y1 comma 1. Ooh, let me get the order right. A y1 comma 1 minus a y1 comma. Oh, let me get my parts in there as well. Theta phi minus a y1 comma minus 1 of theta and phi. Right, so in order to get it to be a real function that we can plot, we have to do some linear combination to get that e to the I phi part to be real. And so we do a combination of the e to the I phi and e to the minus I phi to get rid of the imaginary part, and this gives us a real function. And then we can do the same thing with the 2py, which we'll call psi 2py, and r theta and phi. Radial part is still the same. Angular part ends up a little bit different. Now it's kind of funny because we're going to have an imaginary times our angular part. y1, 1, theta and phi, plus y1, minus 1, theta. It turns out when we do this addition of the y11 and the y1 minus 1, you get something that has an I in it, you multiply by I, and then that gets rid of the imaginary part. You end up with a real portion. Because you get an I sine theta. So that gets rid of the I in the sine theta part. The important thing here is we can take these different solutions that we've been talking about, and we can relate them to our atomic orbitals. This is just hydrogen, right? So we can start to make plots. Right, we can go up to the 3Ps of the 3Ds. We can start making plots like our old pictures from Chem 124 where we were doing when we were first learning about electron configurations. At this point, where we have not brought in the idea of spin-orbit coupling or other energetic terms, our energy is just dependent on the n value. So the n equals 1, I'll have the same energy. The n equals 2, I'll have the same energy. The n equals 3, I'll have the same energy. It's not going to stay that way for long, but right now, that's okay. And what we did with these old pictures is we put electrons in them. Ta-da! And we put it as a half arrow pointing up. Is this all familiar? Why did we do that? Yeah, so there's a couple different things going on. First off, we put it in the lowest energy state because we were only talking about ground state electron configurations, right? When we were first learning about this, we were just like, oh, let's do the lowest energy version of it. And then we did the arrow pointing up, and we usually do it as a half arrow pointing up because electrons have this thing called spin associated with them. That represents a spin-up electron, and we have to have some sort of function associated with that. So there's a wave function associated with this, which is really difficult to talk about. Right? And we use these really funny kind of notations to talk about it. And the reason it's difficult to talk about this is there's no classical analogy we can make to this. I can't write down a nice function for what it means to be spin up or spin down. So we just talk about psi of alpha or psi of beta, where psi of alpha is going to be our spin up case. That would be a value, well, I'll talk about that in a moment. These have values associated with them. This psi of beta would be a spin down case. And now spin, this is the part where it gets a little bit strange. Spin and all of its associated properties are separate from our other nuclear properties. So the L values we've been calculating, the M sub L values we've been calculating, those are, when we're talking about a molecule, those are referred to as orbital angular momentum parts. So that L we've been calculating has been the orbital angular momentum, and it turns out this spin is going to have spin angular momentum associated with it. So we have to have a new set of operators to deal with this idea of spin when we want to start talking about things that have electrons. Question?
Oh, when you say spin, it's not like a spinning thing, right? That's like
no. Right, so it turns out, so when we start looking at this, it's really weird, right? So a couple things happen is if we do the SZ operation on psi of alpha, so that is getting the Z component of this. If you do the SZ operator, now what's the SZ operator do? Right? It operates on spin to give us the Z component of the spin. The shorthand of doing this is we essentially say our SZ operation on a psi of alpha or beta is just going to give us the m sub s value and that function back. So it just gives us whether it's pointing up or pointing down. Now the nice thing is, since electrons only are spin up or spin down, we really only end up with those two possibilities. It's either plus a half or minus a half. The other nice thing about this is if we do the integral of psi alpha star, psi alpha, again, sigma is some made-up coordinate that we have to work with in spin space. So if we integrate over all possible spin space, it's normalized. And if we do the same thing, but we do our psi alpha, psi beta, they're orthogonal. So it's an orthonormal basis set that, again, like, why? There's no classical analogy for this. So right now we're pretty much just doing definitions of how these things work. Right? We've got this idea of electron spin, lots of experimental observations, lots of theory, lots of people working on this. They come up with these kind of definitional ideas. What kind of different eigenvalues can we get out of this thing? They're ortho, they're normal. All of these things come out just from the definitions of how we work with this. Okay. This means now when we want to talk, oh, sorry, questions. Question here and then back there.
What's S of Z again?
S of Z is some spin operator. I have no equation to write down for it. Other question?
What's sigma in this example?
Sigma is some spin dimension.
So just a general
Spin dimension, right? No classical analogy for it. I can't point to something and be like, it's like X. It's spin dimension. This is a property of electrons. Now, here's the way I talk about this in my 124 class. I'm going to talk about it the same way here. Here's the weird thing about it, and I'll get back to the question of, is it actually spinning? First off, spin is a terrible word for this thing, but it's what we've used for many years. It's like saying the electron has mass, right? We got the mass of the electron written down on an equation sheet, and no one stops and is like, wait, why does an electron have mass? I thought it was a distributed blah, 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 right? And it's like, it's just a property of the electron. It's been observed, and we know it's true. The electron has charge. Why does an electron have charge? Well, you're getting at some really deep, fundamental, like, how do things exist type questions if we want to start talking about why an electron has charge, which are really interesting to ask, but really difficult to get into. It's like relativistic quantum mechanics with field theory. Like, I wish I knew how to do that stuff. But through these different applications, you can get the idea of charge and mass directly from equations. Spin. Electrons have spin. It's just like charge and mass. It's another property of the electron. And spin is a terrible word for it. Now, the reason it was called this is because it was recognized that it had some angular momentum associated with it, right? We could get some angular momentum associated with it. We can do right? If we do the s squared operation on it, we get the s value squared. It's got some angular momentum associated with it. So this gave people like, well, how do you have angular momentum? Well, everything we've seen that has angular momentum is something that kind of spins around. It also has some magnetic moment associated with it. And so the way people explained this idea of it having a magnetic moment and angular momentum was to say, well, if it was like a ball with the charge of the electron on the outside of the ball spinning around, that would have angular momentum and it would create a magnetic moment. So it's like a basketball spinning, where all the charge is at like the outside of the ball. Now, we've talked before about the classical analogy delusion. If you calculate the size, the approximate size of an electron and its magnetic field, it would have to spin at about 4 times the speed of light. So it's not an object that's physically spinning, right? This is just we call it an intrinsic property, like mass, like charge. It's just there. And our job as scientists, biochemists, chemists, physicists, people in the world, is to look at the world around us and say, okay, well, how can I make these observations and then try to come up with some sense of what's going on? How can I come up with some framework to understand this? And hopefully that framework will let me understand further ideas about it. Okay, so we put it in this lower state because we always go to the lowest energy. And then we put it in this 1s state. We can write this as a different function now. So instead of just being the 1s, this is going to be our function for this is going to be the 1, 0, 0 alpha, which is going to be the R10 of R, the Y00 of theta and phi, and the psi of alpha. The easier way we write this down is we just call it 1s alpha. Technically, there is nothing to prevent us from saying that 1s beta 1s beta would also be a fine solution to this. We put the spin up for a particular reason when we go to these higher states, but in this hydrogen atom, essentially what we're looking at, spin up or spin down is going to be essentially equivalent to each other, unless we apply some magnetic field or do something else to it. But if we just have an electron around a nucleus, alpha or beta would both be valid answers. Now, here's where it starts to get, that's ground state, lowest energy. Now we can start to talk about, what if we wanted to excite this? What if we wanted to put energy into this, and we wanted to send this electron up to a higher energy state? What if we wanted to go to, what if we wanted to go to psi equals 2? Sorry, n equals 2. What happens in that case? Well, we end up with several different choices. We essentially have the 2s alpha, the 2s beta, the 2px alpha or beta, the 2py alpha or beta, the 2pz alpha or beta. We end up with 8 different choices. We get the 2s alpha, the 2s beta, the 2px alpha, the 2px beta, the 2py alpha, the 2py beta, the 2pz alpha, or the 2pz beta. So which one does it go to? To get to the short of it, to get to where the final thing is these 8 possibilities. Only particular choices are going to have a non-zero probability. And that is to say, when I do some integration on these things, there's only going to be certain answers that have probability of happening. All the others are going to have 0 probability. And what we have to understand is there's a couple rules we have. So as we go, our change in our S value is going to be 0. That is to say, if it's already in alpha, it's going to keep being alpha. Or so when we move this electron up, it's not going to flip. It's going to stay in the alpha state. In order to have a non-zero, right? If it flips, we end up with a 0 integral. So that's one thing. We're also going to have our L value, our orbital angular, so this is spin angular momentum, doesn't change. Our orbital angular momentum can change by a value of plus or minus 1. So that is, if we're in the S state, it has to end up in a p orbital. If we're in a p state, it can go to a d orbital or an s orbital, but it can't stay p. This is a consequence of the fact that when we shine light on something, the light itself has angular momentum. And if we're going to have conservation of angular momentum, delta L has to change. We can get into, I don't have time to do the integrals, but we will do the integrals when we'll look at this with more detail on Tuesday. But there's one more thing. And I'm going to define this one more thing before we end class. Delta J plus or minus 1. What the heck is delta J? Right, so it turns out when we're looking at this, delta J, right now that we've got spin angular momentum and orbital angular momentum, we need to talk about how those two things come together. For this idea of total angular momentum, J is going to have different possible values. Its maximum value is going to be L plus S. Its minimum value is going to be L minus S. So essentially, 1 through 5 vector algebra, or vector math. Zeros to ones. Okay. If I have one line and I put it, if I have one line pointing in a direction, I have another line pointing in a direction, they add up. If they're pointing in different directions, they subtract from each other. That's all we're doing. Right? So my orbital angular momentum and my spin angular momentum can be pointing in the same direction and add together, or they can be pointing in different directions and subtract from each other. Now, I wish I had about 15 more minutes, which is, but man, I should have ended that quiz sooner. No, I shouldn't have ended that quiz sooner. But questions before I let you all run away?
What's the point of doing that? S is always 0.
S is not always going to be 0.
It's delta.
The delta S is 0, right? Okay. So right now, our S is 1/2.
Gotcha. Okay.
So the change in S can't happen.
Okay.
Our J value can be something besides 0. Can be now what? And this is also this thinking. We're going to do this for 1 electron on Tuesday. Then we're going to increase it to 2 electrons in these lower states. Then we're going to do 2 electrons in higher states. And we're going to start finding, the thing we're going to, if you want to get ahead, is we're going to start looking at term symbols to give us ways where we can do this to figure out which transitions are allowed and which transitions are not allowed, spectroscopically speaking. Other questions?
What is the M sub S in the, when you're doing the spin operator?
Oh, M sub S is just it's like M sub L, but for electrons. So it's only plus or minus 1/2. Okay.